All right, I figured it out. I had a temporary lapse in memory. All right, now the property is the logarithm of a plus the logarithm of b is equal to the logarithm of a times b. Now, to prove this, let's suppose that the logarithm of a is some value big A, and the logarithm of b is some value big B. Let's get out of the way. All right, now, presupposing this means that e to the big A is equal to A, and e to the big B is equal to little b. So, that means that the logarithm of A times B is equal to the logarithm of e to the big A times e to the big B, which, as we know from the properties of exponentials, e to the A times e to the B is equal to e to the A plus B. So that means that this is also equal to the logarithm of e to the quantity A plus B. And because of the definition of a logarithm, we know that this is equal to simply A plus B. But remember that A is equal to the logarithm of little a, and b is equal to the logarithm of little b. So this is actually equal to the log of little a plus the log of little b, which shows that the log of little a plus the log of little b is exactly equal to the log of little a times little b. That's one property of logarithms. Now, this argument applies only for log base e, because I used e here. But if you had a different log base here, it'd be the same thing. You just substitute a different base in, you'd get exactly the same result. So this is a general property. It doesn't matter what the base of the logarithm is. Now, as you would expect, this exact same argument applies. The logarithm of a minus the logarithm of b is equal to the logarithm of a over b. Which, given this first property, you could extrapolate the second property pretty easily. It's pretty obvious. You just change a power from a positive power to a negative power, and you get the same thing. The next property is that the logarithm of x to the a is equal to a times the logarithm of x. Now, let's imagine that the logarithm of x is equal to some value big Q. I don't want to differentiate between a little x and a big X because they look the same. And the logarithm of x to the a is some power big P. P. We're going to call it P. All right. Now, the logarithm, or now, this means that e to the big Q is equal to x, and e to the big P is equal to x to the a. Now, this one here, e to the big P, is equal to x to the a. Well, all we have to do is take both sides to the power of 1 over a, and we wind up with e to the big P over a equals x. And therefore, and we know x is equal to e to the q, therefore e to the p over a is equal to e to the q. Therefore, q is equal to p over a, or p is equal to q times a. Or the logarithm of x to the a is equal to a times the logarithm of x. The fourth property that I want to go into with logarithms, the last one of these little logarithm gymnastic techniques. This one isn't used quite so often, simply because most of the time in physics you're dealing with a log base e. But essentially it's still really the same principle. And what this principle, what this essentially is if you're dealing with a logarithm, if you want to use a logarithm in a different base, this is called the change of base formula. And what this allows you to do is most calculators only have, like this calculator, I think this calculator only has log base e. It might have log base 10 too, because that's sometimes used. But most calculators only have log base e and often log base 10, because those are the only ones that are commonly used. But if you want to use another base for the logarithm, there's something called the change of base formula. And what this says is the logarithm base b of x is equal to the logarithm base b of x is equal to the natural logarithm of x divided by the natural logarithm of b. Now, it doesn't have to be natural logarithm. You could also have the log base b of x is equal to the log base a of x over the log base a of b. You could do that as well, but most of the time that's not useful. You have the natural logarithm right on the calculator. It's the one that everybody uses. It's the most common one. I suggest that you just use that. That's all you have to do. Now, I'm going to finish up by discussing some of the limit properties of the logarithm. Now, the logarithm of x. All right. What does the logarithm of x look like? Well, I'm going to ignore the negative side. Typically, you call the function the logarithm of the absolute value of x to avoid this problem. Right now, we're just going to discuss the logarithm of x. If we're going to discuss the logarithm of x, then that means that the logarithm of negative numbers is imaginary. Because if you can't take a number, a positive number, to a real power and end up with a negative number. You can take a positive number to an imaginary or complex power and end up with a complex number. So you can get negative numbers, but that requires bringing in imaginary exponents. And that's, again, outside of this level of discussion. Okay, now, properties I want to discuss are logarithm of 1, the limit as x approaches 0, plus. Now we put this little plus here. What this means is as x approaches 0 from the right-hand side. The limit as x approaches 0 minus would mean from the left-hand side. Now, if these two are not equal, then we say that a limit doesn't exist. We could say that the left-sided limit is this and the right-sided limit is this, but the limit itself doesn't exist because all approaches have to yield the same limit. So it's kind of allows us to still have some idea of limits without really having limits. Now, so I want as x approaches 0 for log x, and the limit as x goes off to infinity for log x. Now, the logarithm of 1. What power do you take e to and get 1? The answer is 0. X to the 0 power, regardless of, unless x is 0, which is, it's weird. If x is 0, 0 to the 0 power is called an indeterminate form. But if it's non-zero, so x to the 0 where x is any non-zero is always going to be 1. So that means e to the 0 is 1. So the power of e that gives you 1 is 0. So that means the logarithm of x crosses the x-axis at x equals 1. Now, before it gets to x equals 1, it's negative. Why? Because remember, e is greater than 1. So you're going to have to take e to a negative power to get something